Hello everyone. Today we are going to cover a crash course over Taylor series and Taylor expansion. And it's a very important concept in calculus. And the fundamental idea is to turn a function, for example, sine x, into a polynomial. We how to do that? We consider the for example, we consider the derivatives of sine x, like the first derivative, second derivative, third derivative, all over to infinite derivative. To be specific, we can first suppose fx is equal to anxn plus an minus 1 x minus 1 plus an minus 2 x minus 2 all over to a1x plus a0. Okay, any polynomial looks like this. And then we consider, since we can typically we expand the function at a point, for example in x equals 0, and we know that when sine 0 should be f0, right? And f0 is equal to a0, and sine 0 is equal to 0, and therefore we get a0 is equal to 0. This is, and then this can be regarded as the zero derivative, right? And we can consider now the first derivative. The first derivative of sine x is cosine x, right? Cosine 0 equal to 1. And in this scenario, this polynomial's derivative f slash x is should at the point of 0 should also be equal to 1, right? And what is the expression of f dash? This is the first derivative is like n minus x to the power of minus 1, and all over to a1, right? If we want to write it in a more formal way, we can use sigma notation. And this is the original function, and we can write it as, because according to the derivative of polynomial, we know it's like this. And in this scenario, let x equals 0, we know that it is all the terms except if it's, yeah, we consider this, all the term except a1 have x, the a2x, right? 2a2x, and all the other terms have x as a term. As a result, those terms are equal to 0, and the only term that left is a1. And that's why we have to, in order to those to the polynomial and sine x to be equal, f dash 0 should be equal to cosine 0 should be, then as a result we derive that a1 is equal to 1. And here we've catch the essence of Taylor's expansion. It essentially is that it is we want every derivative of the original function to equal to the polynomial, and the key is that we can do any like any derivative easily because it's an polynomial, and all the other terms, if we expand at x equals 0, all the other term will be 0, and the only term left is the final term that is there's no x. And we can then expand another the next step, right? Cosine 0, cosine 0, we may kind of write down the derivative of sine x, cosine x, right? And the negative sine x, negative cosine x, yeah. And for the third one, which is negative sine x, we know that negative sine 0 is 0. But we know the second derivative of x should be like something, a lot of term times x, plus we know it's like this one a derivative of f dash x again, and this is eliminated because it's a constant, right? And the only thing left is 2a2, right? And if we let x equals 0, we get 2a2, and 2a2 should be equal to f at dash 0, which is 0, and 2a2 is 0. We get a2 is 0. And then we can look at the next term. It's the you can further keep on going, and the key observation is, let's quantify it. For the we find for the an, we want to determine an, this coefficient of the polynomial, and our method is to find the nth derivative of x. And then this should be another polynomial, right? And then we let x equals 0 because we expand at x equals 0 at that point. And in this scenario, it will be like a kind of x, many terms times x plus an y, while the the in at the start, this term should be like this, right? An times x to the power of n. But after getting through nth derivative, n times of derivative, it become the first derivative makes it like become this, right? And the second time it becomes this, and the third time it becomes this. And after n times, you can expect that it should be, after n times, it should be n's factorial times an times x to the power of 0, which is n factorial an, right? As a result, for the nth derivative of 0, all other terms are 0 except this term, which is n factorial an. And what we want to determine is the every coefficient of fx, right? And now we got the formula of an. N can be every number, every natural number, right? As a result, we get the final conclusion is that an should be equal to fn 0 or divided by n factorial, and n can be every. Maybe I should choose another another letter. It's not appropriate to use m here because I also denote the highest power, highest term as m. Maybe we can rewrite as ak. Yeah. And we've got the Taylor's expansions formula, which is fx should be equal to, for example, if if we write it at the form of the summation, we get it is equal to like in the original form is like this, right? And we substitute our formula of AR. It should be r's factorial over f r's derivative times 0 times xr, right? This is the Taylor's expansion at a point x equals 0. And you expand it at any point you want, but remember, if you want to uh, expand at any point, you have to use x minus r to generate the same, which is essentially to first uh, transform the function a little bit, and you got the same effect. And that's how we've get the important formula of Taylor expansion. And for example, and as a result, we can expand sine x, which is x minus 1 over 3 factorial x3 plus 1 over 5 factorial f5 minus 7 factorial f7. We can because well, the reason why we would like to expand the sine x cosine x ln e1 plus x, those kind of function, is that their derivative form some rule. For example, sine x derivative, as we've mentioned, is periodic, right? And that's why it's easy to expand it. Yeah, that's how Taylor's expansion works. You have to understand how we derive this formula. Yeah.